In this lecture of T and L beams, I will discuss how to analyze the T and L beam and how to design the T and L beams. Here is the capacity analysis steps. So for the questions, the data we are given, that is width of the beam, depth, BW, FC prime, FY, area of steel, that all things are given. We have to calculate how much is the capacity of the beam, means how much is the flexural capacity of the beam, 5B Mn. Let me, okay. Step 1. First of all, check that whether the slab in tension or not. If the slab is in tension, then we will design the beam as a rectangular section. That is the first case for the T and L beam. If our slab is in tension, then we will design as a rectangular beam. And second step, for the if the slab is not in tension, okay, so if the slab is in compression, then we will go in the second step. For second step, first of all, we assume that the neutral axis lies in the flange. That is the analysis procedure step. First of all, we assume that the neutral axis lies within the flange. Okay, we will calculate the A as by assuming that the section is rectangular. A as Fy over 0.85 Fc prime B, and then we'll calculate the neutral axis depth C. And if our assumed value C is less than HF, our assumption is correct, then the beam will be designed as rectangular beam. Okay, we have assumed that if the first of all, we have just placed that by assumption that the neutral axis lies within the flange, and if after getting the value of C neutral axis is less than the thickness of the flange, then our assumption is correct, then we will design the beam is as a rectangular section. And if that C value is greater than HF, and if the C value is greater than thickness of flange, then the beam will be designed as T beam. Then first of all, we will calculate ASF, area of steel, to balance the compression, the flexural compression, the compression force provided by the flange. ASF, that is 0.85 beta 1 HF FC prime over Fy B minus BW. Then to get the ASW, okay, the second component, total steel minus ASF, that will be ASW. Now we will calculate the revised value of A. Okay, A will be calculated ASW Fy over 0.85 FC prime BW. Then we will calculate the strain S and phi factor. Okay, if our A is greater than the A that is required for the row max, okay, then we use phi 0.9, and if change, then we have to interpolate the phi value for the other values. At the end, for the flexural moment capacity, force into lever arm, here phi will be, if that will be tension controlled, 0.9, that is the web steel Fy into D minus A by 2, the steel required for the compression to balance the compressive force in the flange, ASF Fy into D minus B1 over B1 into HF by 2 for under reinforced section. So let's start for the example number 1, that is a T beam. Data is given. We have to determine the flexural capacity for the two cases if the slab is in the compression. Okay, that in the question that is mentioned that slab is in compression, then we have to go for step 2. First case of steel, if area of steel that is 3900 millimeter square, and if the area of steel 3000 millimeter square, we will check for the both cases. Example 4.3, that is the same example that I have shown in the slides. Example 4.3, a T beam has the following data: B, effective flange width, that is B 800 millimeter, effective depth 450, BW, here the web width 350, H, that is the height of the flange or thickness of the flange, concrete grade 20 megapascal, grade of steel that is 420 megapascal, slab is on the compression side. Okay, then we have to calculate the design flexural capacity for the following two cases. As area of steel, if the area of steel that is 3900 millimeter square. Second case, if the area of steel that is 3000 millimeter square. The solution, case 1 that is area of steel that is 3900 millimeter square. First of all, we will assume that considering the neutral axis within the flange. When we consider the neutral axis within the flange, we consider the beam as a rectangular beam. Then we will calculate simple as Fy, our 0.85 Fc prime B. Okay, 3900 grade of steel, grade of concrete, and the web effective width that will be B will be used. Okay, we have considered that the neutral axis lies within the flange. So we got the value of A 120.5 millimeter, and when we have calculated the value of C, A divided by beta 1, we got the value of C, that is 141.7 millimeter. We got the result, and that is greater than H. H means height of the flange, so neutral axis lies outside the flange, means we have made the assumption and that assumption is incorrect, so our C lies outside the flange. So then we will calculate ASF, that is 0.85 beta 1 H Fc prime Fy B minus BW. Okay, all the data is given. So area of steel that is required to balance the compressive force produced by the flange. So the area of steel that is 1935 millimeter square. To get the value of web, so total steel minus ASF, we get the ASW 1965 millimeter square. Now we get the revised value of A. Okay, 1965 multiply 420, 0.85 Fc prime BW. Here we will use the BW. A 138.7 millimeter. Now we will check that that will be tension controlled or not. Beta 1 3 by 8 D, so 0.85, 0.375 multiply 450, so we got the answer 143.4 millimeter. Our A is less than AL, that is A is the the witness equivalent stress block depth that is required for the tension control. Okay, our A is less than this, so that is the tension control. We will choose the phi value 0.9. So to get the moment capacity, simple formula, ASW into lever arm, ASF means TSF into lever arm. So ASW we have calculated already, 0.9, 1965 a grade of steel, D 450 minus 138.7 divided by 2 plus 0.9, 1935 ASF Fy 420 D minus beta 1 0.85 multiply 125 divided by 2, and the whole formula is divided by 10 power 6 to convert into kilonewton meter. So we got the moment capacity 573 kilonewton meter. Now for the second case, okay, you have seen in the T-beam analysis that is too much simple as compared to the other beams. So case 2, area of steel is 3000 millimeter square, considering the neutral axis lies within the flange. Same procedure. A will be calculated, as Fy, our 0.85 Fc prime B, and the full effective width will be used. We got the answer 92.6 millimeter. A divided by beta 1, that is C. So you can see in this case C is less than H, so the beam will be designed as rectangular beam. Okay, so beam will be designed as a rectangular beam. So here the moment capacity will be calculated. Same formula just as we do in the singly reinforced beam, as Fy into D minus A by 2, 0.9, 3000 multiply 420 multiply 450 A minus 92.6 divided by 2. and you can see we have used the value of 0.9. Why? The A will be remain same, beta 1 3 by 8d, the value is 143.4 millimeter. So our A is less than this, so we will use the factor 0.9. And the for the rectangular section design, area of steel 3000 into the grade d minus a by 2, we got the answer 457.8 kilonewton meter. So that's all for the analysis of T beam.